Hello, everyone. Thanks for joining me again. So last lesson or last video, we had a quick look at conventional electric current, moving charges, and how moving charges do cause magnetism. Okay, and the magnetic field is circular around a, a f- in a flowing around a flowing charges in a wire, and it's circular around, if a charge q was moving in this way, then it would cause a field that was circular around it. Okay, now this charge, let's say if it's a proton or it's a positive charge, would, if this is the way it's moving, then this is conventional current. And so I can use my right hand grip rule to say that, oh, it's a positive charge moving this way, and so the field would be clockwise. And so if I did draw that arrow like I've drawn it, I would be correct in saying this is, sorry, that's a bit, that this is the right way around that wire. Okay, it isn't the opposite way. It isn't this way. It is not that way. Okay, it's not the opposite way. All right. So today we're going to have a look at solenoids and what happens if you coil a wire, and what is the actual, what's the amount of, I don't know, magnetism caused by a current carrying wire. How do you quantify that? Okay. Alrighty. So this is our waste outcome that we're looking at. Current carrying wires are surrounded by magnetic fields. So we know this, and we know that they're circular for a straight current carrying wire. If it's just like this, then we know it's going to be circular. Okay, the magnetic field. This is at 90 degrees, by the way. So I'm drawing it kind of in 3D. If I was looking at in 2D, the magnetic field would be going would be at 90 degrees to that. Okay, it would be at 90 degrees. So even though it would be circular, it's into and out of the page at 90 degrees. Okay. All right. These fields are utilized in solenoids and electromagnets. Okay, so electromagnets are those types that we can turn on and off. Now this is interesting. Okay, so if you think about this, if we have a bar magnet, which is north-south magnet, we can't turn this off. Okay, this is permanently on all the time. We can't turn this off when we want it. This is permanently on. It's never off. Okay. However, electromagnets use this ability of a current carrying wire to create a magnetic field, but these can be turned off, okay, when we want them, because we just turn off the current. Okay, you just turn off the current to turn off the magnetic field. Okay, so electromagnets are magnets which use the flow of charges or electricity to be created, okay, to create that magnetic field. Okay, so let's have a think about this. So we know how if there was a current carrying wire, and this is conventional current, then we know that, using a right hand grip rule, that I'm going this way, and so my field will be curving this around clockwise into and out of the page, which would look like, and I can draw it with dots and crosses. Okay, so it's going clockwise around like that, and so at this point I would have a dot. Okay, and then it would go around, and then I would see the bottom of that field, and then it would come around again. There would be dot, cross. Okay, that's what the field around that current carrying wire would look like. Okay, if you had the same in opposite, conventional current going down, then the field would look like this. It's going around this way. So so you would draw it so that at this point it will be coming out of the page, at this point going into the page, which is a cross, out of the page, into the page, out of the page, into the page, out of the page, into the page. For the length of that wire, okay, there'll be circular fields all the way along. All right, so we're happy with that idea. So my question to you is, well, if we want to make a stronger magnet, a stronger electromagnet, because this is a magnet that's created using the flow of electricity or the flow of charges. Okay, we can do a couple of things. Okay, we can increase. I'm sure you can see straight away that you can increase the current. Okay, so we can say that the magnetic field strength, that's B is the magnetic field strength, magnetic field strength. Okay, and this is measured in Teslas. That's the unit, Tesla, capital T. Okay, Tesla is proportional to current. Okay, and surely you could also say that, well, it's proportional to also the number of wires that you have together if they're aligned in the right direction. Okay, all right. So let's have a look at how solenoids utilize this sort of idea. Okay, so a solenoid is essentially a coiled wire. Okay, let's go green. All right. Now, let's start off with the coiled wire, and then we can look at how to make a solenoid even stronger. So let's look at this. So firstly, why coil the wire? This is the question. So a straight wire produces a circular magnetic field. That's where we looked. And it weakens as you move away from the wire. So we know this, okay? So it's not too strong. It's not very strong. In a single loop, the magnetic field is magnified in the center, but it's still not strong enough. So if we loop the wire once in a circle, I don't actually like that explanation, but anywho, by twisting the wire, then goes on to say, by twisting the wire into a large number of helical coils, a magnetic field of a permanent magnet can be stimulated. And it's strong enough to replace permanent magnets. Okay, so let's see how they do this, okay? Okay, so I'm going to draw a solenoid. A solenoid is an electromagnet which uses coiled wire. Okay, and I'm going to draw the blue. I'll draw this current carrying wire in black. Okay, so you can pretend that the one end of this is coming in and it's coiling around. It's coiling around and the last coil is coming down like that. Okay, and I'm going to say that the current in this wire is going in this direction. Okay, so the current in this wire is going in that direction, so it must be leaving in this direction. Okay, there's two ways to find out how this magnetic field acts. It turns out that this solenoid actually acts like a bar magnet, and we'll see why. Okay, we'll see why. So we found out that this current carrying wire, this individual little bit of wire, will have a circular field around it. Okay, and the current is going this way, downwards, you can see, and we're seeing this side of that magnet. And so I don't know if we can, maybe we'll draw it in gray. And so you can agree with me that you will have a circular magnetic field around all of these wires on this one side. On the opposite side, you'll have the same. On the top, you'll have the same, etc., etc. Okay, so you'll have this happening here, all right, and I'm like that. Okay, so what happens is, in essence, on this side, you get all of these mini magnetic fields are all going the same way, so they reinforce and they act as a big magnetic field, okay, in that direction. You can see that that's what's happening, okay, all right, and on the other side they do the same, but the field is going opposite, so you get it's going this way, okay, and it's going like that. Okay, and it happens at the top and the bottom too, but we're just going to draw, we're kind of drawing into and out of the page. This is one side, this is the other side of that solenoid. Okay, so as you can see, it looks like a north-south bar magnet. When we coil wires, together with a current flowing through it, because the individual currents going through the little sections of wire create their magnetic field, and they all reinforce in this way. Okay, so you can actually replace this. If you replace this with, if you could equate this. I'm going to write this is equivalent to a bar magnet, and now we can see. Okay, well, if you had a bar magnet and you had a field going like this, and like this, what type of field would it be? Well, you can say that, well, look, it's going from north to south. So this is the north pole of the solenoid. This side is the north pole of the solenoid, and this side is the south pole of the solenoid. Okay, because it acts like a bar magnet. So this is one way that you can very easily. So obviously today you've learned that if you coil a wire, the more coils you have, the more stronger the magnetic field will be. But you've also learned that if you do coil a wire, the magnetic fields of the individual current going through that small sections reinforce to make a bigger magnetic field around the solenoid, which is a coiled wire. Okay, so a coiled wire creates a magnetic field that that is exactly the same as a bar magnet. Okay, now the next question is how do you know? So how do we know which side of a coiled wire or a solenoid, is north or south? Okay, which one acts like the north or south? So there's two ways of doing this. There's two ways. The first way is the logical way, which I just showed you here. Okay, you would say, okay, on this side, the current is going around this way. Okay, so if that's the beginning of the coil, and this is this is going around like that, we know the current is going around. Sorry, actually, I'll re-look at this. Okay, so if we look at that there, and you look at a coil of wire, at this point on this side, the current is going down. Okay, and if you use your right hand grip rule, current going down means a clockwise field around it. And so if we drew that field, it would be coming like this into and out of the page in a circular direction. Okay, so the field around that would be going in that direction. So we can say that therefore, if lots of coils would therefore produce a field going this way. Okay, clockwise around that point. Okay, and then you can say, well, that looks awfully similar to a bar magnet, and a bar magnet, if the field was going like this would be the north pole, that would be the south pole. Okay, the other way of looking at it, the second way, is to look at the solenoid from one side. Okay, so this tells you how to do that. So the second method is you look into the solenoid. Okay, so you look at one end of the solenoid. That's the first part. Okay, and then you look at the direction of current. Look at the direction of the current. Okay, so in our example that we just drew, if I was to, so in this method here, okay, I would look into this side of the magnet with my eye. Okay, what would I see? If I do that, I would see that's the circular solenoid, okay, going into the page, and this is my eye. I would see the wire, and I'm going to draw this in black. I'd see the wire coming up from this end and then going around that here. Okay, all right, so in this end I would see the current going clockwise. Okay, so this current, so then I draw a circle and I'd say the current is going clockwise. The current's going clockwise. And what does this look like? So if I draw a little arrow here and I draw a little arrow this way, you can say that this, if you join up these, this looks like an S. Okay, so this would be the south side of the magnet, because the current, if you look at that, so an S, the end of it, you put tails on the end, and that's going clockwise. Look, the arrows are going clockwise. Okay, so that's the current is going clockwise. Okay, so the next thing you can do is what would happen if I looked at, well, okay, so what would happen if I looked at what would happen if I looked at with my eye this other side of the solenoid? Okay, well then if I'm looking at the other side of the solenoid, I would see a circle there, and I would see that the wire would be coming around like that and then exiting downwards, and so the current would be going anti-clockwise. Okay, so if I draw the current going anti-clockwise, okay, this is what it would look like. That's the current going anti-clockwise. And so a north, if you look at it, if you put tips on the ends, it looks like this. Okay. So and it reinforces what we just found out. That is indeed the north side, and the other side was indeed the south magnetic side. Okay, so you can do it either by looking at the way the coils go around the solenoid, or you can do it by logic. Okay, either or. Now, don't beat yourself up if this is a little bit tricky. This is the first time you're seeing this. We'll go through this in quite a lot of depth. Okay, and the last thing I'll leave you with is the fact that um, for solenoids, it's just a coiled wire. Okay, you can increase, and this is really important, the magnetic field strength. And these are often questions that come up in your ways. You can increase the magnetic field strength in a number of ways. Okay, so how do you increase the field strength of a solenoid? Well, one obvious thing is to increase the current flowing through the wire. Okay. The other thing is you could keep the current the same, but you could increase the number of coils. Okay, the number of coils you have will mean that there's more mini magnetic fields around the little sections of wire, and then that means that you know you have a bigger field. Okay, so you could increase number of turns or number of coils. The same thing. This is the same thing. Okay. Also, there is one other way. So that's one way. There's another way. You could introduce a ferromagnetic core, a ferromagnetic core. Okay, ferro means iron. Okay, if you've got a ferrous material, it's or ferrite is usually called, it's iron. Okay, all right, so it's an iron core. So if you actually put a bar of iron, okay, if you put an iron bar, I'm going to use my chemistry skills here. Okay, if we use an iron bar and we coil a wire around it, that's bad. Anyway, you get the point. If you coil a wire around it, okay, then you will increase the magnetic field strength, and you can look at why that happens. Okay, is there any other way that we could increase that field strength? So we've increased the current. We could increase the current. We could increase the number of coils. We could introduce a ferromagnetic core. I think that's about it. Okay. And solenoids are called electromagnets as well. So solenoids are a type of electromagnet because you can turn them on or off. You turn the current off and they're no longer working as a magnet. Okay. Thank you, guys. That was very good. And I will put up, and you should definitely do these questions here. Okay. And next lesson, we'll have a look at this. How much magnetic field is produced by current carrying wire. Thanks, guys.